Hello, welcome back friends. So in the last session, we have started with the unit number 3, that is transient state heat conduction. So what do you mean by transient heat conduction that we have seen in the previous session? So those who have missed the previous session, please go and watch the previous session to get the proper understanding of the basic concepts. So what do you mean by transient heat conduction? So in transient heat conduction, the temperature is a function of what? It is a function of location and it is the function of time. So what you can see that the temperature, it is continuously changing with respect to time. Later we have seen what do you mean by lump parameter analysis. So for lump parameter analysis, what we have seen one example. We have seen this is a copper ball we have seen, and the temperature of the copper ball, it is uniform throughout. So what we can say that if the temperature is 70 degrees at a particular point, here also the temperature is 70 degrees. So at any location, that is the change of temperature with respect to time for all the points is same. Means what is happening? We have what is happening over here, that the change of temperature with respect to time for all the points, it is same. So this is nothing but the lump parameter analysis. So now there should be some particular parameter to check whether the system is behaving as lump system or not. So that parameter is nothing but the Biot number. So we will see what do you understand by Biot number in the coming sessions. Why we need to study this Biot number? Because it is not every time possible to take a thermometer and measure the temperature at each and every location. So there should be some analytical concept to judge whether the system is behaving as a lump system or not. So the answer to this problem, it is given by the term Biot number. So we will see it in the coming session. So today we will focus on the transient conduction in solid with K tends to infinity. So just I will read out what is written over here. The lump parameter analysis is based on the assumption that the solid possesses infinitely large thermal conductivity. So this is the assumption that is made in the transient heat conduction equation. So the internal conduction resistance is so small that the heat flow to or from the solid, it is controlled by convection. So what is this? We have seen this in the previously in the fins also, that the thermal resistance, it is inversely proportional to your thermal conductivity. Right? We have seen this previously in the fins in case of ideal fins. So if your K value tends to infinity, okay, if your K value tends to infinity, what will happen? Your resistance will be very less. So when your resistance is very less, what will happen? The temperature you will find the temperature uniform at all the locations. So for lump system analysis, we consider that the material is having infinite thermal conductivity, that is very large. So when this K value it is very large, automatically your resistance offered will be very less. So this is the assumption that we have made. So let's see what is again given over here. Now consider this body, okay, this body. So consider a body which is at an initial temperature of Ti. So let the body be at the initial temperature Ti, right? So let this be the temperature, and it is exposed to the environment T infinity, and it is exposed to the environment T infinity and the heat transfer coefficient as H, right? So here you can say that Ti it is greater than T infinity. Now due to this what is happening? As Ti, here what is there? Ti it is greater than T infinity. So what will happen? The heat will flow from the body into the environment, as heat always flows from high temperature to one which is at a low temperature. So the heat will flow from high temperature body to a low temperature one. So what is happening? The heat is flowing out from this body into the environment by what? Convection. Here we are assuming that conduction is very less. Why? Because of the K value, it is tends to infinity. So the heat is moving out into the surrounding by which mode of heat transfer? By convection mode of heat transfer, right? So we have already seen in the previous session that when heat is added to a body, if this is the body, when heat is added to a body, what is happening? The internal energy, it increases, But on the other hand, if the heat is removed from the body, the internal energy it reduces. So this concept we have already seen in the previous session. So this body it is losing the heat to the surrounding by the mode of convection. So what I can say, due to this heat transfer, the internal energy of the body keeps on decreasing as the time progresses. Okay, so this one thing you please keep this in mind, very important assumption based on the previous session. So let the surface area be A, let V be the volume, rho be the density, the thermal conductivity of the body be K, C be the specific heat, let Ti be the initial temperature, and the surrounding temperature you can consider as Ta or T infinity, it's up to you. So now this is the body. So this body it is at a temperature of Ti, and the surrounding it is at a temperature of, say for example, Ta. So now this body it is losing heat, right? That is E out. So this body it is losing heat to the surrounding by which mode? Convection. So what we have written, relating the rate of change of internal energy with convection heat transfer. So what is, how the heat it is moving out? E out, that is nothing but Q convection. So now as the heat it is moving out, what is happening? The internal energy of the body it is decreasing. That's why we can write this rate of decrease of internal energy, that is equal to rate of convective heat loss from the body. So as the heat it is moving out, the internal energy of the body is reduced. As the internal energy of the body is reduced, we can measure this by decrease in temperature. Okay, due to this the temperature will decrease. So minus rho Vc dt by d tau, that is change of temperature with respect to time. Tau it is nothing but time. That is equal to rate of convective heat loss from the body. So all of you know the convection equation, HA delta T, that is nothing but T minus TA. So T is a particular temperature. So why we have inserted this minus sign over here? Because the internal energy it is reducing. That's why we have substituted the minus value. Right? Now all of you know that we can write down the rate of change of internal energy as what? mCp dt. How this equation has come? So as the energy it is moving out, the internal energy it is decreasing. So the term here used it is rate. So rate of decrease of internal energy is what? mCp dt by d tau. So how can I write m? I can replace this m by the term rho multiplied by v. So that's why I have replaced this equation as rho v dt by d tau. So this one thing you are supposed to understand. Now what I will do, I will just rearrange this equation for simplicity. So what I will do, I will take this T minus T infinity to TA to this side, that is dt upon T minus TA, that is equal to HA. I will take this term now to this side. Okay, just simple rearrangement, rho Vc, and I will cross multiply this T tau here. I will take this T tau to this side. So I will get this equation dt divided by T minus TA, that is equal to minus HA rho Vc d tau. Now what I will do, I will take the integration of both the sides. So this term it is constant, so this will be automatically out of the integration. So integration of dt divided by T minus TA, that is integration of 1 by T, it is nothing but log T. So log of T minus TA, this is a constant, so this will be out of the integration, and integration of d tau it is nothing but tau, okay, plus C1, the integration constant. So now what is our aim here? Why we are doing this? For what? We are doing this to find out the temperature distribution equation. So this is our aim now, right? So this is our aim, temperature distribution equation. So we have got C1 now. So how will you find out C1? We will find out C1 from the boundary conditions. We have usually seen this in the previous lectures. So for finding out the value of C1, we will again use the boundary conditions. So initially at time tau is equal to 0, okay? Initially at time tau is equal to 0, what is your temperature? what is the temperature of the body? The temperature of the body will be nothing but Ti, that is nothing but initial temperature. So at tau is equal to 0, that is just when the system has started. So at tau is equal to 0, what is the temperature? Temperature, it is nothing but Pi. So what I will do, I will replace this tau. I will put this tau value over here in this equation. So this term, it gets equal to 0, and I will replace this T by Ti. So what I get? Log of Ti minus Ta, that is equal to C1. So in this way, I have got the value of C1. That is our aim. So now what I will do, I will substitute the value of this T1, C1 in this equation. So that is log of T minus Ta, that is equal to minus HA rho Vc multiplied by tau plus this value of C1, log of Ti minus Ta. Now what I will do, I will take this term, okay, I will take this term to this side, to the left hand side, right? So what I get, log of T minus Ta minus log of Ti minus Ta. So after doing this, what I get, this is the formula, log of T minus Ta divided by Ti minus Ta, that is equal to HA rho Vc multiplied by tau. So if I want to remove this log sign, what I will do, I will take anti-log. So to remove this log sign, I will get T minus Ta, that is divided by Ti minus Ta, that is equal to this whole term now will be nothing but e to the power, or it can be written as exponential minus HA divided by rho Vc multiplied by tau. So what is this? This is nothing but your temperature distribution equation. Okay, so here you can see from that the temperature of the body falls or rises exponentially with time, and the rate depends upon the parameter HA divided by rho Vc. Now this quantity rho Vc divided by HA is called as the thermal time constant, and it is having the unit of time, that is nothing but the second. So here you can see this, what is this equation? This equation we have seen. So this is nothing but the temperature distribution equation. From this equation, what you can find out? You can find out the temperature of a body at a particular time t, small t. Okay, what will be the temperature of the body, for example, after 5 minutes? What will be the temperature of the body after 10 minutes? So you can find out from this equation, the temperature distribution equation. So here what we have seen, that the temperature distribution equation, that is temperature rises or falls exponentially. Okay, so it is clear that you can see this from the graph. Okay, if you see this graph, no, just at the bottom I will show you. If I draw a graph of temperature versus the time, okay, so this is the cooling curve. So initially the temperature will be high, and after some time, say 10 minutes, the cooling will the temperature will fall. So here you can see the temperature, it is falling. So this graph is nothing but temperature versus time. So initially what you will find, that initially the rate of fall of temperature, it is very high, that is the slope dt by d tau, it is very high. And as you move, okay, as the time increases, the slope almost it becomes tangent, right? So this is nothing but exponential fall of temperature. So what we can say, that the temperature, it is initially the fall of temperature, it is very high. See from this graph you can see that the temperature, it has fallen to a much higher value in just small time dt. Why? Because initially the temperature difference, that is, for example, the atmospheric temperature is 25 degrees and this temperature, it is, say for example, this is 40 degrees. So initially the temperature will fall quickly, say from 40 to 30, okay, in a small time interval t. But as you progress, for example, if you come at this point, so here the temperature will be what? Here the temperature will be 28. So from 28 to, if you want to reduce to 25, it will take too much time. Okay, why? Because here the temperature difference, it is very less. So this is clear from the equation, that here the temperature, it is falling exponentially. Okay, it is written over here, that see, I will just read out. initially the rate of cooling is very high, since the rate of heat transfer is very high due to large temperature difference. I have told you that initially what is happening, the temperature, it is falling quickly because of the high rate of difference between the temperatures. But as the time progresses, the rate of cooling decreases. What is the rate of cooling? It decreases. That is, the slope of tangent decreases. So this is the tangent, no? So the slope decreases because of the temperature difference between the body and the fluid decreases. Here the temperature, it is decreasing. So during the end of the cooling, the body will take a lot of time even for 1 degree drop in temperature. Okay. So at the end, for example here, see the temperature drop, it is very less, but the time here you can see the time, this is time, it is taking too much time, but initially this is not so, right? So what conclusions that we can draw from the equation, that this is the temperature distribution equation, the temperature rise or fall exponentially. And one more conclusion you can draw from this equation, that larger the value of HA divided by rho Vc indicates that the body will approach the environmental temperature quickly. So if this value it is higher, okay, HA divided by rho Vc, if this value it is higher, then the body will approach the environmental temperature quickly. Okay, so these are the important conclusions that we can draw from this equation, right? So I hope you have got the clear understanding of the equation. So various numericals will be based on this equation. So till then, keep watching. Happy learning. Thank you all of you.